then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, Precalculus students. Welcome to lesson number 13. Today we're going to investigate discontinuities further. We're going to look at how to find removable and infinite discontinuities, or also called vertical asymptotes, from an algebraic standpoint. So our analysis today is not going to be based off the graph of the function, but based off the equation of the function. Okay, today we're going to continue our exploration of continuity and discontinuities. Today we're going to be focused on removable and infinite discontinuities, or removable discontinuities are also called holes or point discontinuities, and infinite discontinuities are also referred to as vertical asymptotes. What I have here is the graph of x squared minus x minus 6 over x squared minus 9. And if you do an analysis of the graph based on what you know, you should be able to tell that right here we have an infinite discontinuity as the graph is shooting towards infinity and negative infinity. And the location of that infinite discontinuity is at where x is negative 3. So you see when x is negative 3, the graph will get extremely close to negative 3, but it will never touch it. And also, what you can't see, because most graphing utilities don't do a good job of always showing removable discontinuities, but there is a removable discontinuity right here at 3. If I click on that point, I'm not hitting right at 3. There I go. If I click on a point, it's going to say, you'll see the open circle, and it's going to say that at 3 the function is undefined. So we're going to look at how we can figure out where our infinite discontinuities and our removable discontinuities are from an algebraic standpoint. So from not looking at the graph, but doing some work on the function itself. So I'm going to use the same function. We are already aware that we have a removable discontinuity at x equals 3 and an infinite discontinuity at x equals negative 3. So let's see how we can find that from an algebraic standpoint. So let's write our function. Okay, so there is our function. And quite honestly, the same work we did to find limits algebraically is the same work we're going to use to find infinite and removable discontinuities. So the key skill, once again, is being able to factor. So what I'm going to do is I'm going to factor my numerator. That's x minus 3 times x plus 2. I'm going to factor my denominator. That's x plus 3 times x minus 3. And then I'm going to see if there's anything I can cancel out, or shall I say remove. And you should notice that I can cancel out this x minus 3. Now, this function has two discontinuities, as you know. It has a removable discontinuity at x equals 3, and it has an infinite discontinuity at x equals negative 3. Now, we know that because we looked at the graph, but even without being able to look at the graph, I'm just looking at this function, I understand that this function has two discontinuities, 3 and negative 3, because those are two values which will make my denominator become 0. So again, the focus for these rational functions is on the denominator, and if you look at your two factors for your denominator, you'll see that there's two values, negative 3 and 3, which will cause your denominator to be 0. So that's telling you right there that you have two discontinuities at x equals negative 3 and x equals 3. In the beginning, it doesn't tell you what type of discontinuities they are, but it tells you do have those two right there. Now, to classify them, if you are able to remove one of those factors that are giving you a discontinuity, that's going to represent, well, the value that makes that factor 0 is going to represent the removable discontinuity. Again, the key to this is that our variable, our denominator cannot be 0. So if you notice this factor that I'm canceling out, x minus 3, that is 0 when x equals 3. So when x is 3, x minus 3 will equal 0. So therefore, since I removed that factor, that means x equals 3 is my removable discontinuity. And again, it's because it will make that factor equal 0. So in short, when you factor the function, the guy that you're able to remove is going to represent your removable discontinuity. Now, when the function is in its most simplified form, as it is here, so x plus 2 over x plus 3 is the most simplified form. Nothing else can be canceled out. When it's in its most simplified form, the value of x that makes your denominator 0 is your infinite discontinuity. So x equals negative 3 is my infinite discontinuity. And the easy way to remember, the guy you remove is removable, and the guy that stands in our denominator, the guy that stands in our denominator is there forever, so it's infinite. So we'll just work through a couple of more examples on the same item. So here, let's say f of x is x squared plus 7x plus 12 over x squared plus 8x plus 15. And the instruction will be find any removable and or infinite discontinuities. All right, so our method of attack is going to be factoring. So again, we should be keen on factoring. And again, if you're not understanding how I'm factoring these things, that's some information you need to communicate with me, and I need to do a refresher course for you on factoring. So the numerator should factor x plus 4 times x plus 3. My denominator should be x plus 3 times x plus 5. And clearly you can see the x plus 3 is going to go, making x equals negative 3 my removable discontinuity. And as you can see, x plus 5 is going to be remaining in my denominator in the most simplified form. So the most simplified form is going to be x plus 4 over x plus 5. And remember, I'm concerned with what makes my denominator 0. So, negative 4 is not an option here. I don't care about the numerator. I care about my denominator being 0. So therefore, x equals negative 5 is the infinite discontinuity. Or also, because on some of your assignments, it'll say find vertical asymptote. So also, or the vertical asymptote. Which if I write again, I'm just going to abbreviate with VA. So these are synonymous terms. So you have an infinite discontinuity, which is also known as a vertical asymptote. You also have a removable discontinuity, which is also known as a point discontinuity. But that's not a term I really ever use, but you may see it other places, and it's also known as a whole, and that's a term I do sometimes use. All right, let's look at another example. So let's say f of x is x squared plus 5x plus 4 and over x squared minus 6x plus 8. So pay pay close attention on this particular example. So I'm going to factor my numerator. Again, I'm finding removable or infinite discontinuities. So I'm going to factor my numerator. That should be x plus 4 times x plus 1. I'm going to factor my denominator. That should be x minus 4 times x minus 2. Now, I should be very careful here because this problem, there aren't any common factors that can be canceled out, because x plus 4 and x minus 4 are not the same thing. So they don't cancel. So nothing cancels. So since nothing cancels, you don't have a removable discontinuity because you didn't remove anything. So your removable was none. You didn't have one. However, so that means that the function now is in its most simplified form the way it already was. And whatever makes my denominator 0 in the most simplified form represents the infinite discontinuity or the vertical asymptote. So I have two of those, one at x equals 4 and the other at x equals 2. So x equals 2 and x equals 4 are the vertical asymptotes, which we can also call infinite discontinuities. And when I write these out, I don't write x equals 2 comma 4, because a vertical asymptote is actually a vertical line, and an equation of a vertical line is x equals some number. So you need to write it out like this. Now for a removable, you can just put the number, of course, because removable really is just a point, but a vertical asymptote is actually the equation of a line. Now let me look at another example. So here, say f of x is x squared minus 25 over x plus 5. Okay, so I'm finding the discontinuities. And so, by the way, these rational functions here, they're not going to have jump discontinuities. I'll show you tomorrow where those jumps are going to come from. But these rationals are only going to have infinite and removables. Okay, so I'll factor my numerator. This will be x plus 5 times x minus 5. My denominator, I can't do anything to it. It stays as x plus 5. And then as you can see, the x plus 5 is going to cancel, which is making x equals negative 5 removable. But in the most simplified form, so if that x plus 5 goes, all I'm left with is x minus 5. So what do you think my vertical asymptote is going to be? You think it's going to be 5? Well, it's actually going to be none. Again, the vertical asymptote or the infinite discontinuity is the value of x which makes your denominator 0. In this example, there isn't a denominator left. So, and let me say that more specifically, it's the value which makes your denominator 0 when the function is in the most simplified form. So x minus 5 is a function in its most simplified form, but it has no denominator, so that denominator will never be 0, and so that's why it doesn't have a vertical asymptote, or what we call an infinite discontinuity. Okay, that's going to conclude this particular lesson, and so you should be able to find infinite discontinuities and removable discontinuities from looking at the function by utilizing factoring. And when you factor, what you can cancel out, the value that makes that factor 0 is the removable discontinuity, and the value which makes your denominator 0 when the function is in its most simplified form is going to represent your vertical asymptote or your infinite discontinuity. See you next time.